bond or one ring. Okay. Yeah. So we got a double bond or a ring. So let's go back up here and go through. We've got one number of signals. So that gives us 3 different types of hydrogens. Integrations, we've got 3 and 1 and 1. And we need to look at the chemical shifts here for a moment. So chemical shift of between 1 and 2, let's look up here at our memorization task, L4.5. We can see in a range of 1.2, the typical ones are a hydrogen that's 3 or more bonds from a functional group. So like we've got this peak that has 3 hydrogens, so it might be typical to this like first one here, where we've got those 3 hydrogens. And then they're bonded to a carbon with other hydrogens. So let's check that out. Yeah, okay. So that might look like, oh, and I need to change my pen type. Let's see if I can erase that blob. Okay, change my pencil type to, okay, so we've got a C with, we've got 3 hydrogens that are all equivalent, so that might look something like this, and they've got 1 foreign neighbor. So I'm going to change my pen color and put my neighbor there in red. Okay, so then let's see, let's go down to this one that's near 10, and let's see if we can find near 10. So 10, 9.7 to 10, that's where our peak is. And look, it's a hydrogen that's on a C double bond O. So really that's an aldehyde, isn't it? Let me write that in. I'm going to put that in green. This hydrogen is an aldehyde. Well, you can hardly see that, but that hydrogen is on a C double bond. So it's an H attached to a carbon as a C double bond O. Okay, so let's draw that in up here. So that's a hydrogen. Again, let me change my pen color and type of pen here. Okay, so that's a hydrogen that's on a carbon. And how many neighbors does that have? It's a doublet. It's got 2 peaks there, so that means it's split by 1 neighbor. So, that's interesting. So I'm going to say, here's a neighboring hydrogen. And that's within 1, 2, 3 bonds. So that's going to split it once. Okay, so that looks good. Let's see what's between 4 and 5. So if we go and look between 4 and 5, 4 to 7 seems to be hydrogens on double bonds. We know we've got a bromine. So where would the bromine range be? If we look between 3 and 4, it says hydrogen, 2 bonds from an oxygen, nitrogen, or halogen. Well, we know we've got a halogen, so let's look at this one. And again, let me change the color here and the type of pencil. So we've got a bromine. So there's our bromine. And the hydrogen that's on the carbon that has the bromine is the one that has the chemical shift around 3 to 4. Well, when we look at our spectra, it's past 4. It's not between 3 to 4. 3 to 4 would be like here, but that's not where it is. It's down farther than that. So that's interesting. Okay, so remember that chemical shifts are additive. So maybe the carbon that has the bromine and the hydrogen, maybe it's close to another functional group. So it's shifting it past the 3 to 4 that we'd expect, past it closer to 5. Well, we do have another functional group on this molecule besides the bromine. We've got the C double bond O. So if we look at our memorization task for a C double bond O, if you look at 2 to 3, there's hydrogens that are alpha to the carbonyl. So there's alpha to a carbonyl. So there's a C double bond O with a hydrogen on the next carbon over. It says hydrogen 2 bonds from a pi bond. So let's look at our molecule. Do we have a hydrogen that's 2 bonds from a pi bond? We do. And it's probably got a bromine on it too. So let's start putting our molecule together. We know we've got 3 carbons, and we've got 4 carbons listed on here. So what about this red one with the red H? Those could be the same, right? So let's go ahead and try that. So we know we've got on the end a hydrogen. And I hate this size pen. Let me change that. Okay, so we've got, I thought I changed the size. Okay, so we've got carbon with an H next to a C double bond O, and then we've got this red hydrogen, and the red hydrogen is next to a C double bond, a H, carbon with 3 H's on it, a methyl group. And let's put our bromine on. So we have C3, H5, 1, 2, 3, 4, 5, oxygen, and bromine. Number of, let's go back, number 1, number of signals. There's should be 3 types of hydrogens. 1, 2, 3. Okay, integrations, 3, 1, 1, 3. And then there's a hydrogen that's on a carbon with a bromine and a hydrogen that's on a C double bond O. So that's 3 different types of hydrogens again. Chemical shift. The H that's on a C double bond O should be down close to 10, which it is. Let's see, the H that is alpha, or 1 away from a C double bond O, plus the bromine on it should shift it further than expected. We thought it would be between 3 and 4, but it's past 4, so that makes sense. Let's look at, the chemical shift for the 3 hydrogens. Notice that they're 1, 2, 3 bonds away from a bromine. So instead of being close to 1, they're almost past 2. They're close to 2, so that makes sense that they're not close to 1, but close to 2, because there's 3 bonds away from a bromine. And then the signal splitting, let's double check that. So we've got 3 hydrogens with 1 neighbor, so they should be a doublet. And we've got 1 hydrogen with how many neighbors? On the left side, we could go 1, 2, 3, and we run into a hydrogen. On the right side, we can go 1, 2, 3, and run into 3 hydrogens. So that's 3 plus 4, let's see, 3 plus 1, equals 4. And how many hydrogens do we think it was? 4. So we're doing good with that. And then 1 hydrogen should have 1 neighbor, and 1, 2, 3, yes it does. So things are looking good. Do we need to check anything else? Down here at the bottom we said it either had a 1 pi bond or 1 ring. Well, we didn't get a ring, so I'll cross that out. And we do have 1 pi bond. It's a C double bond O, so you can write that in. And that matches with the chemical shift of a hydrogen around 10 ppm. Okay. I think if we re-verify our atomic C3H5BrO, if we add those all up, I think we'll double check to make sure we have 136. So you could do that really quick too. And then let's go ahead and put a circle around our final answer, and we have double checked and triple checked our work, and I think that is the right molecular structure that matches the information in both the mass spectrometer